Hey stats students, today we're talking about lesson 10.2, which is errors in hypothesis testing. Yesterday we learned about the null and the alternate hypothesis, which the null is like our initial claim and the alternate is a claim that is competing with that initial claim. Well, when we run a test, we're gathering evidence that suggests one or the other is more likely or supported by the data. However, there's always a possibility that we can make an error and choose the wrong hypothesis incorrectly. So let's talk about a type 1 error. A type 1 error is also called a false positive. Okay. And a type 1 error is rejecting the null when in reality, it's true. And the probability of a type 1 error is denoted by alpha. We've seen alpha before. It's the area outside of the confidence interval. And it's similar. So alpha is the symbol we use to denote the type 1 error. Alpha is called the level of significance of the test also. So a test with alpha level of 0.01 can be said to, have a level of significance of 0.01 or to be a 0.01 test. Just like we had some common confidence levels, we have common alpha values. These are pretty much the ones we're going to be sticking to. And that is that alpha can equal 0.01, 0.05, or 0.10. And remember, alpha is the probability of a type 1 error, false positive. Okay, we can also make, or possibly make, a type 2 error. And this is a false negative. Okay, so this is failing to reject the null. When the null is actually false. The probability of a type 2 error is denoted by beta. So now let's get into some characteristics of a type 1 and type 2 error. Alpha is something that we can control. We can kind of choose, we can adjust it. Alpha is something that we have control of. Beta is not. Alpha and beta, or type 1 and type 2 errors, have inverse relationships. So that means as your alpha value gets larger or increases, beta decreases, and vice versa. As beta increases, alpha decreases. So the higher probability of a type 1 error, the lower probability of a type 2 error. The lower probability of a type 2 error, the higher probability of a type 1 error. In an ideal world with an ideal circumstances, we would have no error on either part, but usually this can only happen through a census. But since usually we can't handle a census, we can't do one, it's really hard to get a hold of everyone in the population, especially if it's a large population. We rely on sample data to help us determine which of the hypothesis is more accurate, which one has more support based off of the sample we've selected, and we could possibly make an error because each sample has sampling variability. So there will be error when working with a sample due to variability. Sample to sample can vary drastically, and it is possible that we pull a sample that is not representative of the population and that misleads us to make, a wrong decision and either a type 1 or type 2 error. It's really important as the investigator of a study that we carefully balance the consequences between a type 1 and type 2 error. So, what if a type 1 error will result in serious consequences? And by serious consequences, we mean like we're going to have illness, we're going to have death, we're going to lose money, things like that. And so if that's going to happen, then we want to reduce that probability of the type 1 error. And in order to do that, we're going to choose a small alpha value. Okay. Same thing. What if a type 2 error results in serious consequences? Well, we're going to want to do the same thing. We're going to want to reduce the probability of a type 2 error. But beta is not something we're in control of. We can't say, oh, we'll just change the beta value. It's not that way. We can control alpha. So we would choose a larger alpha value to offset a smaller beta value and reduce the probability of a type 2 error. All right, let's do some examples. Pizza Hut is marketing a new product, Bigfoot Pizza. This new product will increase sales by more than 14% based on the sales information of a random sample. Mu denotes the mean percent increase in sales for all Pizza Hut restaurants. Consider using sample data to decide between the null hypothesis that the mean percentage increase is 14%, or the competing claim, the alternate, that the mean percentage increase in sales is actually greater than 14%. Is Pizza Hut's conclusion consistent with the decision to reject the null or fail to reject the null? Well, their conclusion is that their sales increased by more than 14%. So based off of what they're saying, they're deciding to reject that null in favor for the alternate. They're saying that it's larger than 14%. At this moment in time, we have no way to verify. We're just practicing with some error. If Pizza Hut is incorrect in its conclusion, is the company making a type 1 or type 2 error? So they believe or claim greater than 14%, but they really are making 14% or even less. And so this would be a type 1 error. We reject the null in favor of the alternate, when indeed the null is actually true. Example 2. Your company markets a computerized device for detecting high blood pressure. The device measures an individual's blood pressure once per hour at randomly selected times throughout a 12-hour period. Then it calculates the mean systolic pressure for the sample of measurements. Based on the sample results, the device determines whether there's a significant evidence that the individual's actual mean systolic blood pressure is greater than 130. If it is, then we recommend, the person seek medical attention. Okay. Let's state the null and alternate hypothesis for this setting. Okay, so the null and the alternate. This is numeric data because if I'm asking you what is your blood pressure, you're going to report back a number to me. So I'm going to use mu, and I know the null is always equal to. And my value is 130, and the alternate is that it would be greater than 130. It says be sure to define your parameters, okay? That is this mu letter that I'm throwing about here. I have to define it. And mu is the mean systolic blood pressure. All right, let's describe a type 1 and type 2 error. Okay, type 1 error would be we reject the null when the null is actually true. So we claim blood pressure is high when in reality it is not. Okay, so we reject the null in favor for the alternate, but in reality the null is true. All right, let's talk about a type 2 error. A type 2 error is we fail to reject the null. So we claim blood pressure is normal, but in reality, it's high. All right, let's move to part C. The blood pressure device can be adjusted to decrease one error probability at the cost of an increase in the other. Which error probability would you choose to make smaller? Okay, so a type 1 error, the consequence here is really wasted time because we would tell someone they have high blood pressure, tell them to come back to the doctor. They would come back and then we'd be like, whoops, just kidding. No, it's not. You're good. Go home. Sorry about that. Over here, if we run a type 2 error, we're going to tell someone that they're perfectly fine, go home, you have no high blood pressure, everything's cool. And then they go home and they're living with high blood pressure untreated, which can really lead to some serious medical problems. So we would really want to reduce the probability of that type 2 error. So type 2 error has worse consequences. So we would choose a larger alpha value. Out of the three we have, we would choose alpha equals 0.10. We would much rather heighten the chances of people just wasting their time and coming back if it meant that we would lessen the number of cases that we accidentally gave a false negative. So for today's lesson, remember the definition of a type 1 and a type 2 error. That type 1 error is denoted by alpha, and we can control that, and type 2 is denoted by beta. They have an inverse relationship. See you tomorrow. Bye.